So, we will start the class, the theory part of this machine drawing. So, in today's lecture, I'll be talking on the temporary fasteners or the temporary methods to join different components. So, in the last class, we have discussed about the permanent joining method. So, one of the permanent joining method as the rivets. So in today's class, we will see the temporary method, how to join different components. So we have already understood the importance of joining because there are very few components which are rarely made in one piece. So different methods are employed to join. The perspective of this course is basically to help you to understand the drawings of these machine elements which are used to join these different components. So I'll share my screen and then we can see other details. So kindly confirm if my screen is visible.
Yes, sir.
Okay. So in case of this temporary joints, what is used is are generally threaded fasteners. So threaded fasteners, they come in this category. And of course, beyond fasteners, we have some joints or couplings like quarter joints and gib joints. So those couplings and joints we will be studying in the next module. In the current module, we will be only focusing on the threaded fasteners. So as we understand from our previous knowledge of threaded fasteners, so threaded fasteners, these are produced using different methods. One of the prominent method is machining method, in which we use a lathe machine and a single point cutting tool, which creates this threaded fasteners or external threads. So what are threads? So threads are nothing but they are, if you see on a cylindrical surface, so these are basically a continuous helical groove which are formed or cut on the surface of a cylindrical on a cylinder. So one method, if we can correctly recall, is the lathe or the machining method, which is used to basically make the threads. And another method which we studied earlier was the thread rolling process. So this is essentially used for making V threads, in which you have basically two dies, and in between you pass the workpiece, and then the dies, they replicate their external threads on the cylindrical surface. So these method basically they produce the external threads. Okay, external threads means the thread that you can see on the exterior surface. Then there are threads which are also present on the internal surface, for example in this nut. So these are produced essentially by tapping. So tapping is the process which is used to create internal threads. So two forms of threads exist. So on this type of arrangement, these are known as the bolts. So nuts and bolts, we have been seeing they are very popular threaded fasteners being used. So just I am here summarizing the manufacturing method, how to make internal threads using tapping and how to make external thread using lathe machine, that is using the threading process and the thread rolling process, which comes in the category of forming process. So beyond these bolts and nuts, there are other methods in fasteners which include screws, and then there are studs. So there is a difference between screw and thread and a stud. So screws generally they are self tightening, means you don't need a bolt here. So the sorry, not you don't need a nut. As in a bolt, you need a nut to basically lock this bolt into in these two parts. So this is part one, which is to be joined. This is part two, which is to be joined. Now all the threaded fasteners, they have this capability that they can be disassembled if you want to remove these two parts. For example, the part has to be removed for repair or maintenance. So in that scenario, these type of fasteners are very useful. So in screws, it is a self-tightening arrangement. The threads, external threads on these screws, they generally lock themselves inside. So In this case, you don't need a nut separately. And then we have studs, basically where you don't have a head. So here you put the nut on the top. So you don't have a head here. So this bolt, this is known as the bolt head. But in case of stud, it is just the cylindrical surface, so there is no head. So where there is less space to accommodate such type of head, so in that scenario we use the stud. But stud, they also have the external threads, okay, similar to the bolt, but these are locked using nut which is placed on the top. And in case of bolt, there is a bolt head which already locks it, and the nut is used on the other end. So fasteners, now we understand these are basically machine components or elements which are used to hold two or more machine or structural parts. So the categories under the threaded fastener include bolts, as we have seen, then studs, nuts, machine screws, set screws, keys, cotter, and coupling joints. So these are some of the important fasteners used till date in with different engineering components. So we will see the technical drawing details of each of them in subsequent slides. So threaded fasteners, they basically are used in different scenarios other than holding the two parts together. So one is this function that we clearly understand, that whenever we want to hold the two parts together, the threaded fasteners could be useful. Then the second scenario in which the threaded fasteners are used, these are basically to adjust the parts with reference to each other. So when we have to adjust two parts, such as we want to just bring the alignment, perfect alignment, or we want to set a particular part in a perfectly on a leveled surface. So in that type of scenario, again, the threaded fasteners are used, as these can be easily loosened or tightened up. So in that scenario where you want to adjust the two parts in reference to each other, this is useful. Then to transmit power. So this is very important. So we have a special category of threaded fasteners which are also useful to transmit power. So if you have driven a vehicle or a car, so you know the importance of a tire jack. So tire jack is a very important tool which comes into play if you want to fix a punctured tire. So in order to basically lift your vehicle so that you can remove the tire from the vehicle, so you will basically put that jack under the proper location beneath the automobile, and then you will basically loosen it up. So all those threads on the tie rod of the tire jack, they are basically the threads which are transmitting power, and they are also helping to lock it there. So it never happens that if there is a load, of course within the permissible limit of the jack, that it comes down. So these threads are so powerful that they lock the jack there, so that you can safely remove the punctured tire and replace it. So in that scenario, even when you are transmitting the power, so they are even holding it at that point of time. So tire jack is one example where you do that. Then the lead screw, of course, on the lathe machine, this is also a example where a threaded fastener or a threaded surface basically transmits power. So power is essentially, what I mean by power here is torque. So in mostly rotational components where you are transmitting power, so it is basically power. Instead of power, it is actually the torque which gets transmitted. And of course the power torque can be expressed in form of power, as we already know that 2 pi nt is the formula by 2 pi by 60. 2 pi nt by 60 is basically the formula for calculating power from torque. So in these scenarios also, the threaded fasteners are used. Now we'll understand what is the nomenclature of these threaded fasteners or a screw thread, because understanding this nomenclature is very important from the perspective of drawing these machine elements, or understanding the given drawing of these machine elements. So generally these nomenclature, they are empirically derived, and they have a specific, each and every word, they carry a specific meaning, and they play an important role in deciding the dimensions of this threaded fastener, any threaded fastener. So first important is basically the major diameter. So major diameter is basically the diameter which is touching the crests. So first we will understand the crest is basically the top. So this point at the top of the any two or more than two the threads. So this point is known as the crest. So this crest is similar uh, in case of the external threads, and the internal threads the crest comes down. Then root is basically the lowermost point where the thread ends, and consequently in the internal threads it is on the opposite side. So nominal diameter is basically the largest diameter. So means it is the diameter which is covering the basically the crests of the subsequent threads. So this nominal diameter is also very important because in drawing, basically the threads are nomenclated using their nominal diameter, not the minor diameter or the pitch diameter. So the other diameters, why they are important? So they are important from the drawing perspective. So from the drawing perspective, we need to calculate the values of minor, major, and the pitch diameter. But the nominal diameter is basically the diameter by which the thread will be nomenclated. So we'll discuss how it is nomenclated in a while. So then things will get more clear. So next is basically the minor diameter of any thread, which is of course the core diameter. So as the name itself is telling, so core means it is basically passing from the lowermost uh, point. So means where the root is of the thread is described. So the diameter at that point is known as the core diameter of the thread. So it is the smallest diameter touching the external of the thread, or if in case of internal thread it becomes for the crest. So if for the internal it just reverses itself. Next very important parameter while nomenclating threaded fasteners is the pitch diameter. So pitch diameter, it is basically the diameter of the imaginary circle where the thread width is equal to the thread gap. So if I'll just draw it again. So if this is the thread, okay. So there can be infinite lines which can be drawn, but there will be a particular line which can be if we draw. So the width of this line will be equal to the width of the gap. So this is the gap, and this is the width of the thread thread teeth. So the imaginary line, so in this case, this pitch diameter will be the imaginary diameter or the line which is passing through this point where the width of the thread is equal to the gap between each thread. So this is known as the pitch diameter. And of course, next comes the very important, another important parameter for the threaded fastener, that is known as the pitch. So what is pitch? So pitch is nothing but it is again the distance measured along the parallel axis. So this is the parallel axis. So distance measured at this point of time at between two corresponding points. So it is either distance between two crests or it is distance between two roots of the adjacent threads. So pitch is also important because pitch basically decides if the threaded fastener is of coarse nature or it is of fine nature, and pitch is of course used in nomenclating these threaded fasteners. So next is another important aspect, that is lead. So lead, what is lead in case of threaded fastener? In case of threaded fastener, lead is basically the distance the screw advances in one axial turn. So you take a bolt and you take a nut. So you mark a point on the nut and you rotate it 360-degree. So the nut will linearly move on the threaded surface of the bolt. So this distance which the nut moves in one rotation is equal to the lead of that particular threaded fastener. So lead will be deciding the distance. So generally this lead is helpful in quickly screwing or unscrewing different components. Then next is basically the flank. So flank is nothing but it is the straight portion. So you see here this slant portion here. So this is basically the portion known as the flank of the threaded fastener. So this is there present on either side of the screw. Then crest, of course, I discussed that in the beginning. So this is basically peak of the threaded head. adjacent flank tops, and root is basically the bottom of the screw thread and between adjacent flank bottoms. And then next important, another important parameter is the thread angle. So thread angle, I'll again draw the zoomed view here. So if these are the threads here, so thread angle will basically this angle between the this two flanking surface of the thread is known as the thread angle. So thread angle is important because the thread angle decides if the thread becomes a V thread or the thread becomes a square thread. And depending on that, the friction characteristics, the power transmission characteristics of the thread, basically they change. Now we come to the drawing part of these machine elements. So again, for drawing, what is most important? It is the most important part for drawing is basically to know the dimensions. So again, these dimensions are empirically derived as shown here. So this is basically the form of thread for a metric thread. So this is a metric thread, means in general the threads which are used for a daily purpose or the general applications, they are the metric threads. So these threads are basically again based on ISO standards, and in India we directly adopt these ISO standards in order to maintain interchangeability. So next important thing to understand is what is interchangeability of machine elements. So interchangeability means the ability to replace the component irrespective wherever it is manufactured. What happened in the World War era, both the different countries were on a path of expanding their industrial base in order to produce weapons and vehicles, military vehicles. So each country developed its own terminology, its own standards, basically to develop the different components pertaining to the wars. But later on it was realized that if a particular component, say a particular gun which is made in say Germany, and it has follows the German standards, and now if it is sold in worldwide, so if some component is not working, or there is a fastener inside the inside that gun, so we want to replace that. So if it is not following the international standard, we cannot change it easily at a different place. So interchangeability was a concept which was introduced after the world wars, so that different things which are manufactured all around the world, they are basically standardized, and then we can interchange it with the similar type of component which is manufactured anywhere. So if you are following a particular standard, in that case, you will be able to produce the part which could be interchangeable with part produced at some different place. So this concept was also introduced in case of threaded fasteners. And this concept, based on this concept, several empirical relations. So empirical relations, as I discussed earlier, are experience based. So these experience-based relations were developed where the pitch of the thread, which will be deciding all other parameters of the thread, including the major diameter, minor diameter, and height of different threads. So this you can use these correlations while you draw the threaded drawings of these threaded fasteners later on. So beyond the metric, this is of course, as I discussed, it is the metric thread. So beyond the metric thread, there are other forms of thread which are still used. So we'll just go through through them one by one. So first is basically the sharp V thread. So sharp V thread is basically the most popular thread used, in which you see the thread surface, it makes a very sharp angle at a 60 degree. So what is important to remember, the angle, the thread angle that I was discussing in the nomenclature slide. So the thread angle in case of the sharp V thread is 60 degree, and the height of each this thread is basically 0.87 times the pitch. So pitch will be generally given. So based on that, this can be drawn. So these threads, what is the application of this thread? So sharp V thread, basically they provide a larger contact area. So larger contact area will basically give more frictional resistance. So wherever we want to lock two components, we don't want the thread to self loosen up. So in that scenario, the V thread will be used. It is used for positioning and the pipe and plumbing work, all that work where we don't want the pipe joints to get loosened up because of the pressure of the fluid. So in that scenario, the V thread is used. So these are self-locking threads. So because the surface area is higher, so the friction is higher between the locking threads, so they can be used for the mentioned purpose. Next is the British standard Whitworth. So these were developed in the Britain, and of course they follow the inches unit. But nevertheless, these threads are also used. The difference here is the thread angle, it gets reduced to 55 degrees, and instead of this sharp corner or the at the crest or the root, we have a rounding effect provided here. So this rounding effect has a radius of 0.14 the pitch. So this is 0.14 multiplied by the pitch of the thread, and this radius is basically helps to make the thread less susceptible to damage. So you can understand if the thread is having this type of a pointed feature. So these type of pointed features, they are more prone to breakage, but the rounded surface, this type of rounded surface, it is less prone to breakage or damage. So this is basically an advantage. So this BSW is also used in that type of scenario where frequent tightening and untightening is there. So instead of using V thread, we'll be preferring the BSW standard thread. Next, of course, is another important form of thread known as the square thread. So square thread, it derives its name from the square pattern or the square profile, where the side of the square is 0.5 times the pitch. So half of the pitch, half of the distance of the pitch becomes the one side of the square. And these type of threads are very ideal to transmit power. So transmit power, so by power I mean torque. And since the flank is almost, it is not almost, it is perfectly perpendicular. So here you see the flank, this is perpendicular to the axis of the fastener. So no radial component of the force can be generated. So if radial component of the force is generated, so generally these things, they try to come apart because of that radial component, and therefore the power transmission efficiency is quite good in these type of threads. So these are also used in screw jacks and all. Next is the buttress thread. So buttress thread is, it basically derives the combined advantage of the V thread. So that is the 60-degree thread which we have studied, and the square thread which was studied in the previous slide. So by combining this, so what happens, one flank becomes perpendicular. This is coming from the square thread profile, and the other is basically inclined at a 45-degree angle. So here, instead of having the angled flank surfaces on both the sides, so angled flank surface is only present on one side at a 45-degree angle. And then the width of this crest is also there, which is equal to 0.16 times the pitch. And then of course there is a slight slant here, we can observe. It is not perfectly 90 degrees, but there is an offset of say 7 degree here. And these type of thread, they basically combine the advantage of square thread, that is they are also good in transmitting power, and at the same time they are also low in frictional resistance, since you have only one surface, one flank surface which is inclined. So in this case, the friction resistance is also quite low. But since you have an angled flank at one end, so you can understand that power transmission can only take place in one direction. So like in screw press, where you are basically pressing or taking up a heavy load using this threaded fastener, where you want the thread to be in self-locking arrangement. So in that case, you want it to easily go up in one direction, but it should not come down under the influence of load. Means in one direction, there it should be easy. In the other opposite direction, it should be self-locking type of a scenario should develop. So in that scenario, the buttress thread becomes a obvious choice. Then Acme thread is the next category. So Acme, basically this name is derived, this basically Acme, the word Acme means here point uh, to perfection. If you see the literal meaning in the books, so this is known as point to perfection. So this is basically what was done in the Acme thread. Basically, the square thread that we studied earlier. So this square thread was modified in this case. And what modification was done? So in the previous case, the modification what was done here is that the trapezoidal ends, the root of the thread was widened up. Instead of, if you compare the crest, so the root of the thread is now widened up. So when you have a wider base, so this increases the strength of the thread. So means higher power can be transmitted. And since the sides both are inclined, so instead of perfectly locking, in case of inclined, their engagement and disengagement is quite easy. So where you want to routinely engage for power transmission and then you want to disengage, so in that case, the Acme thread, which is a modified version of the square thread, is more preferable. Of course, other dimensions of this thread, for example, the height of the crest will, sorry, the width of the crest is 0.37 times the pitch. And of course, the depth is zero point 0.5 times, and the base is also zero point 0.5 times the pitch. Next is basically the worm wheel. So worm wheel or worm thread is again used for used in similar scenarios as the Acme threads, but the depth in case is higher. So here the depth was 0.5 p. So here the depth is 0.69 p. So you can understand where the depth increases. So the engagement between these threads while transmitting power, so the level of engagement with this penetration, as the penetration increases between the threaded surfaces, so the power transmission capability or the torque transmitting capability, it increases. So worm thread is typically used in that type of scenarios. So now I'll just share with you the real life examples where these threaded fasteners are used. So as I discussed earlier, so there is a screw press. So in the screw press, generally what we do, we rotate this handle, and then basically what we are doing is we are trying to press it or applying force to some material which is kept below. So all this thread which is there are basically some form of threaded fastener. Essentially, these are square threads. Then jack screw, as I discussed earlier, this is used, very helpful tool to use in case of changing a tire for a vehicle. Then of course the lead screw is there where the torque get transmitted. So this lead screw is there in the carriage of the lathe machine. So carriage is basically part of the lathe machine. And then worm and worm wheel, as we have seen just now. So worm and worm wheel. So this is basically the worm. This is known as the worm, and this is known as the wheel, worm wheel. So again, the idea here is to transmit power. So the one axis, one shaft is passing like this, which is on which this worm wheel is keyed. So this is rotating, and then the motion is transmitted to this shaft. So you see, non-parallel, non-intersecting shafts in such scenarios where if you want to transmit power, so this type of worm and worm wheel arrangement is used. And again, the threaded type of a fastener or threaded joints are basically used here to transmit this power. So these are just very few examples which highlight the importance of these type of scenarios or this type of applications where the threaded fasteners are used. So what we have covered till now is what are threaded fasteners, what is the different forms of threaded fasteners, which essentially include the nut and bolt, then screws and studs. Then we have seen what are the different types of threaded fasteners being used. For example, the V thread is there, square thread is there, buttress is there. We have also seen to some extent the scenarios, in which scenario you will pick which one. So this knowledge is of picking up the right threaded fastener is very important for an engineer, because when you are designing any component or you're designing any product, so based on the movement, based on the requirement, you have to suggest to the manufacturer, okay, that you have to select the buttress thread or you have to select the square thread. So when is this going to happen? This is only going to happen when you have the prior knowledge, okay, like this type of thread will be useful here in a particular scenario, and this type of thread will be useful in a different type of scenario. So the idea here is to give you an overview, like what are threaded fastener, what are different types, and how they are used in real life examples. With this background, moving ahead, we go to the thread designation. So thread designation is basically the designation which will be used on most of the machine drawing sheets. So thread designation is basically a coded version in which gives all the information about the thread. So in the isometric thread, the diameter pitch combination is used to designate the thread. So I'll discuss how this is done. So this is done by placing the capital letter M followed by the nominal diameter, which of course you can consider equal to the major diameter, and the pitch in which both are separated by an X. For example, if it is mentioned like this, M10 cross 1.25. So what this implies? So this implies that it is a metric thread, a V type thread, okay, a metric V thread. Then what 10 is signifying? So 10 is basically signifying the nominal diameter. So what is the nominal diameter? As we discussed, we can consider this nominal diameter equal to the major diameter. So why this nominal diameter is important? So this nominal diameter is important. Suppose you have this scenario. So you have these two plates which have to be joint uh, using the uh, thread. Sorry, the threaded fastener. So this two plate which has to be joined. So what you will do? First you will drill a hole. So as discussed earlier, to place the fastener, you have to drill the hole. So once the hole is drilled, so the selection of the drill bit, what will be the diameter of the drill bit? So that diameter of the drill bit will produce the hole of that particular diameter. So that nominal diameter, why it is important? So nominal diameter of the bolt is important, or the fastener is important, because it will be encasing or filling up that threaded or the hole. If the nominal diameter is smaller than the hole diameter, so you can understand the joint will not be tight joint, it will be a loose joint, and there will be lot of play between both of the two parts. So if there will be play, so different vibrations, if the part is kept on some moving, it is in a moving or a dynamic scenario, so this movement will cause lot of vibration, and these vibrations may even prone the fastener to get failed or fractured. So knowledge of this nominal diameter is very important. And of course, then what is present after this X is basically the pitch. So this is the pitch. So we have understood that pitch is basically the distance between two corresponding crest, sorry, two adjacent crest or two adjacent roots of the thread. So for a metric, this is the nomenclature, or the sorry, this is the designation that you are going to find on a engineering drawing or the machine drawing for any component. So for example, as shown here, if it is M10 cross 1.25, so 10 by 10, looking at this M10, you will quickly recall that it is a metric V thread with nominal diameter as 10. So means if the whole diameter which is produced, this whole diameter should also be equal to 10. So you cannot use this 10 M10 in an 11 or 12 millimeter hole, because it will be loose. It will not create a tight joint, and then basically the joint efficiency will reduce, and it may also cause failure of the joint. Of course, it is obvious that the if the joint is of the diameter is higher, then it cannot go inside that hole. So if no pitch is mentioned, so in certain cases, what may happen that we may omit the presence of the pitch value. So this is then considered to be as the coarse pitch. So that is a standard pitch which is generally not mentioned, but in case of fine pitch, the pitch value has to be specifically mentioned. For other threads which are beyond the metric V threads, so you can see how the nomenclature goes by. So for example, this, if the nomenclature is mentioned as SQ 40 cross 10, so this indicates it is a square thread. with a nominal diameter of 40 millimeters and pitch as 10 millimeters. So now by reading this nomenclature, you can get an idea what does it mean on a drawing. So in drawing, in the machine drawing, you will not be able to figure out if, oh, it is a V thread or it is a square thread. So by looking at this nomenclature, you will be able to figure out, okay, this is the right screw, this is the right bolt I have to pick to make this component. Similarly, for Acme thread, we will write Acme 40 cross 8, which indicates it is an Acme thread with the nominal diameter 40 and pitch as 8 millimeters. In certain cases where finishing means the surface of this the thread is to be produced in a very precise way. So in that case, what we do is we also add the tolerance component. So we will discuss later on in this course what is tolerance, sometimes mentioned as 5h, okay, or it may be mentioned as 5 small h. So this type of this component mentioned here, or this one mentioned here. So in case this h is capital, or so this goes for internal threads, okay, and if it is a small or in the lower case, so this goes for external threads. So this is what this is the factor of tolerance. So I'll just briefly touch upon what is tolerance. So tolerance is basically the acceptable deviation in the dimension of any manufactured component. It is not possible in any scenario to precisely manufacture any component to the same size every time. Each and every time when you do the manufacturing for any component, in this case we are discussing about threaded surfaces, it is not possible to repeat that dimension precisely same every time. So in each component we give a acceptable deviation. For example, I am producing this nominal diameter as 10 millimeter. So if it is M10, so this diameter is 10 millimeter, but sometimes this diameter may be 9.95, at times it may be 10.05. So I will specify that this is the tolerance range. So something falls beyond this will not be accepted. Something falls beyond this will not be accepted. So what happens? This tolerance is also specified in certain cases, again by continuing it beyond this standard designation as 5H, 5G is there. Then of course there are other nomenclature for tolerances which we will see later on. But just for your information, I'm mentioning here. And another important point that I want to mention here is with respect to the pitch. So as we have discussed, this is known as the pitch. So pitch is also equal to 1 over threads per inch. Threads per inch, also called as TPI. It is also known as the TPI. So why this is important? So whenever you are producing threads on any machine, so generally what we have to specify is number of threads per inch. So number of threads in 1 inch, how many threads will be coming? So that will basically give us some idea about the pitch of the threaded fastener. Higher is the number of thread in a given inch. In 1 inch, higher number of threads are there. So this means the pitch is very small. And if the number of threads is less, of course the pitch will be on the higher side. So this is another important thing which has to be understood, that thread is also pitch of any threaded fastener is equal to 1 over thread per inch, also abbreviated as TPI. This is TPI. So I will stop here for today, considering this is a bit long session on the threaded fasteners. So now I'll take up questions from you to discuss the content that we have just covered. So please feel free to ask the questions. Yes, if there are questions, please feel free to ask. So I understand there is a quite anxiety among you that this software is not yet available. But I have again checked today, so I think by end of this week, by Friday, you will definitely have the access to the software. So once you have the access to the software of SolidWorks, I will provide with you the practice assignments which you have to do and submit on the submission date. So that will help you to basically understand how you have to go about drawing the different components. What we have discussed till now is the essentially some exercises will be there based on the riveted joints, then isometric orthographic projections, and some exercise will also be there on threaded fasteners. So this I will not give all the exercise in one go. Of course, I will give you time to become accustomed or to know that software first. Then only the assignments will be given. But once the software is available, I will suggest please put in some extra effort from your end to learn the software in the minimum possible time, so that we can go ahead with understanding the next part of this course, which is of course about the assembly drawings, in which we assemble different components together to form the given engineering component. So definitely by Friday you will have the access to the software, and then I'll also another important thing is the practice tutorials for the software are already uploaded in the practical lecture link which are provided in the Moodle. I strongly suggest once you install the software after it is made available, please try to repeat at least what is being done in the tutorial, so that you become more familiar with the different options, different menus in the software, and later on that will help you to draw your own regarding the assignment or exam. So please, if there are any questions, we can take up the questions. If not, so then we can close this lecture and we will continue this in the next class, that is in the next week. Yes, are there any questions?
No, sir.
Okay, so then if not, we will then close the class. Thank you for your attention.
Thank you, sir.